Hi everyone, we will continue solving the questions. The following figures show 2-point charge of 1 microcoulomb and the distance between them is 2 meters. Calculate the amount of the electrical field at a point on the line connecting to the two charges that at 0.5 meter from the first charge and 1.5 meter from the second charge. It is showing. First, when we are writing the given, this is R1 and R2, Q1 and Q2. Only we will change micro, its meaning 10 power negative 6. And also constant number K, 9 multiplied 10 power 9 meter square multiplied Newton over coulomb square. Now I am writing the equations. Main equation, electric field equals constant number Q over R square. But we have the two, we will writing using the Q1 and Q2 and R1 and R2. Firstly, E1 equals K multiplied Q1 over R1 square equals, I am writing the number 9 multiplied 10 power 9 Q1 equals 1 microcoulomb, it's meaning 10 power negative 6 coulomb over R1 equals 0.5 square equals 36 multiply 10 power 3 unit is Newton over coulomb for Q1 charge. Secondly, we are using K Q2 R2 square equals, I am writing the number 9 multiplied 10 power 9 multiplied 10 power negative 6 over 1.5 square equals 4 multiply 10 power 3 Newton coulomb for Q2 charge. Now we are finding the resulting or net electrical field. Result equals first electrical field minus second equals firstly 36 multiplied 10 power 3 minus 4 multiplied 10 power 3 equals 32 multiplied 10 power 3 Newton over coulomb, our result. Let's continue. The electric flux. The relation between the electrical flux and electrical field as it is showing the figure. I will show the formula. The electrical field in a particular area depends on the density of the electrical force line passing by that area. So it increases as the density increases, and therefore the density of the electrical force line is a measure of the electrical field. The electric force line that intersect the surface perpendicularly is called electrical flux and symbolized, or we can showing this figure. Do you remember? Electric flux, we can using the equation electrical flux equals electrical field multiply area. or the plate they are passing the electrical field. Let's watch the videos.
Electric flux. The electric flux through a surface held inside an electric field represents the total number of electric lines of force crossing the surface in a direction normal to the surface. Electric flux is a scalar quantity and is denoted by phi. Consider flow of a liquid with velocity v through a small flat surface ds in a direction normal to the surface. The rate of flow of liquid is given by the volume crossing the area per unit time v ds and represents the flux of liquid flowing across the plane. If the normal to the surface is not parallel to the direction of flow of liquid, that is, to v bar, but makes an angle theta with it, the projected area in a plane perpendicular to v is v ds cos theta. Therefore, the flux going out of the surface ds is v bar dot n cap ds. For the case of the electric field, we define an analogous quantity and call it electric flux. We should, however, note that there is no flow of a physically observable quantity, unlike the case of liquid flow. In the picture of electric field lines described above, we saw that the number of field lines crossing a unit area placed normal to the field at a point is a measure of the strength of electric field at that point. This means that if we place a small planar element of area delta S normal to E bar at a point, the number of field lines crossing it is proportional to E delta S. Now suppose we tilt the area element by angle theta. Clearly, the number of field lines crossing the area element will be smaller. The projection of the area element normal to E is delta S cos theta. Thus, the number of field lines crossing delta S is proportional to E delta S cos theta. When theta equals to 90 degrees, field lines will be parallel to delta S and will not cross it at all. Thus, the area element vector delta S bar at a point on a closed surface equals delta S n cap, where delta S is the magnitude of the area element and n cap is a unit vector in the direction of outward normal at that point. We now come to the definition of electric flux. The electric flux delta phi through an area element delta S bar is defined by delta phi equals to E bar dot delta S bar equals to E delta S cos theta, equation 1, which, as seen before, is proportional to the number of field lines cutting the area element. The angle theta here is the angle between E bar and delta S bar. For a closed surface, with the convention stated already, theta is the angle between E bar and the outward normal to the area element. Notice, we could look at the expression E delta S cos theta in two ways. E delta S cos theta, that is, E times the projection of area normal to E bar, or E perpendicular to delta S, that is, component of E bar along the normal to the area element times the magnitude of the area element. The unit of electric flux is Newton meter square per coulomb. The basic definition of electric flux given by equation 1 can be used in principle to calculate the total flux through any given surface. All we have to do is to divide the surface into small area elements. Calculate the flux at each element and add them up. Thus, the total flux phi through a surface S is phi approximately sigma E bar dot delta S bar equals to sigma E bar dot delta S bar, equation 2. The approximation sign is put because the electric field E bar is taken to be constant over the small area element. This is mathematically exact only when you take the limit delta S tends to 0 and the sum in equation 2 is written as an integral.
Let's continue. Example. Calculate the electric flux through a charged and isolated spherical conductor that's radius is 1 meter and there is a 1 microcoulomb charge on a surface. When we are writing the equations, our equation, if you remember, we are using the first E equals K and Q1 over R square. First we will find E because of our electrical flux equals electrical field multiply area. But it is giving micro, we must change micro to coulomb. Micro is meaning 10 power negative 6. Also, the radius is 1 meter for spherical conductor. We must find the area of spherical conductors. First, we are finding the electrical field equals 9 multiply 10 power 9 multiply the charge is 1 micro 10 power negative 6 over 1 meter. It is giving 1 meter square equals 9 multiply 10 power 9 multiply 10 power negative 6 equals 9 multiply 10 power 3 or 9,000 Newton over coulomb. Now we find electrical field. Our equation electric flux equals 9 multiply 10 power 3 multiply the area. The spherical conductor area we can using the 4 multiply pi multiply r. We can using the our r square equals pi. We can accept equal 3.14. R equals it is given 1 meter. 9 multiply 10 power 3 multiply 4 multiply 3.14 multiply 1 power 2. When we are multiplication this equation we will find 1.13 multiply 10 power 5. The unit is Newton multiply meter square over coulomb. The unit of the electrical flux. Let's continue. Example 2. An electric charge of positive 2 multiply 10 power negative 6 coulomb was placed in a homogeneous electrical field that show a force of 8 multiplied 10 power negative 2 Newton. What is the amount of electrical field? Our equations: E equals F force over Q. We know force, we know Q. Equals, it is giving force equals this one is, and charge equals this one is. I am writing the number. Force 8 multiplied 10 power negative 2 over 2 multiplied 10 power negative 6 equals 4 multiplied 10 power 4 or 40,000 Newton over Coulomb. Answer is